Oh, good afternoon, everyone. Welcome to our virtual number 6. Our lab today is on chemical equilibrium and Le Chatelier's principle. I hope you have covered or you have started chapter 15 in your lecture. That is the chapter on chemical equilibrium. Some chemical reaction, most chemical reaction you have encountered or you have seen in the text has an arrow separating the product and reagents. Essentially, those types of reaction, we say that at the end of the reaction, all the reactants are consumed or converted to products. However, there are some reaction which at some point the product will decompose to form the reagents. And at that point, the concentration of the reagent, the concentration of the product do not change. At that point, we say that the system is at dynamic equilibrium. I want to share my screen and show you what is meant by a system at dynamic equilibrium. Before I come back to Le Chatelier's principle, a system at dynamic equilibrium is indicated by a generic equation, for example, all right, P and A reacting to form C and D, you'll see a system at dynamic equilibrium shown using two arrows pointing in the opposite direction, means the system at dynamic equilibrium. C, C, and plus D and D. I'm just picking up some hypothetical reagent and species in this case. The lowercase letter stand for the coefficient in the balanced equation. This will be applicable in the next lab, all right? You know what the coefficient means from the balanced equation. Now, it is important to note the physical state of your reagents and product. Always pay attention to the physical state. When it comes to writing the equilibrium expression for the next lab, or even for your lecture, you should be able to, see species participate or are used in writing the KC value. I'm not going to get into that, but today we want to look at systematic dynamic equilibrium. And with respect to Le Chatelier's principle, you see here, Le Chatelier is a scientist who came up with a principle, and you should be able to state its principle. I've marked some of the pre-lab, and I saw that you're doing good. You know how to define the Le Chatelier's principle. A system at equilibrium first, right here, when we say a system at equilibrium, it means forward reaction. We call this forward reaction. And this is reverse reaction. When the rate of forward reaction equals to the rate of reverse reaction, we say that the system is at dynamic equilibrium. We say system, all right, system is at dynamic, all right, dynamic equilibrium. At that point, we say that the system is at dynamic equilibrium. With one arrow, that means there will be no, essentially no reagents after the reaction is complete. Now, Le Chatelier came up with a principle which states that when a system at equilibrium, such as this one, is subjected to some external stress, all right, the system will respond in such a way that it will offset the stress, it will offset the stress. There are different words used in defining or stating Le Chatelier's principle, but it all boils down to the system of setting the stress. I've underlined the word stress, all right? I've underlined the word stress so that you should be able to know what stress means. Right here, I'll write the stress you should be able to identify in a problem. Here are the stress or the condition. Let me just say stress. Not the stress we normally go through when you're stressed out, but the stress here is up. I have about, I'm gonna break it down to about 7 or 8. One, all right, this is a change in what? Change in, when I use this, you know what that means. It means concentration of the reagents or reactant. Let me just put reactant. That to here, change in, all right, product, change in product concentration, all right. It could be, when I say change, I should have broken down this into, let me break down into specific reagent, maybe increase in, let me just break down to increase in reagent concentration, and then there is the decrease in reagent what? Reagent concentration. 3 here, there is increase in what? Increase in product concentration. There is 4 here, decrease in product concentration. There is another stress here, 5, change in volume, all right. It could be increase in what? Increase in pressure, and this goes hand in hand. This applies to gases, reagent, and product. Pressure applies to gases in the dynamic equilibrium. You can increase the pressure, all right. 6 here, let's say change in what? Change in temperature, change in temperature. And change in temperature, you have to pay attention whether it is what? Whether it is exothermic reaction, and there is endothermic reaction. These are the 2 types of reaction you got to pay attention when you are looking at the temperature. I have another one here you should read on your own for the sake of your, lecture exam. There is adding a catalyst, and I've seen also adding inert gas into system in gaseous equilibrium. This is a catalyst. 7 is adding a catalyst. All right. I'm not going to talk about all of them, all the stress. So when we say system at equilibrium is subjected to some stress, what are the possible stress we are talking about here? These are the stresses you should pay attention to. Now, if a system at equilibrium, such as this one, let me use this for the sake of explaining the stresses I talked about. If we increase any of these reagents in A and B, the system will shift away from what you are adding. So when you are adding something into, all right, it is shift away from what you are adding, and make sure you read the physical state, or pay attention to physical state, because some question might be like, oh, all right, you are adding a solid into already a solid reagent. Solid do not affect the dynamic equilibrium. Now, it will shift away from what you are adding. So in terms of stress, if we increase the reagent, it will shift away. So I'm going to use an arrow here, which indicates that it is shifting away from what you are adding. Likewise, if we increase the product on this side, it will shift away from what we are adding. So increasing the product concentration, it will shift towards left. When you see the arrow, it shifts towards the left. Either you use an arrow, okay, or you state that it will shift towards left or towards right. So left, right, you can use an arrow. So increasing a reagent, it will shift away from what you are increasing. That's how I look at it. Now, when we look at this, if we are removing the stress here, or rather subjecting the system at equilibrium to some stress by removing either B or decreasing the concentration of B, it will shift towards what you are removing. So here, if I'm decreasing the reagent, it will shift in this direction to replenish what you are taking away from the system. And likewise for the product, it will shift towards right, because you are removing a product, and it will try to replenish what you are removing in this system. So if we remove C, if we remove D, the system will shift towards the product. If we are removing any of the reagent, it will shift towards what we are removing to replenish that. So here is the summary of change in concentration of either the product or the reagent. That is what we will be studying in this lab. There are two activities, all right, or two stresses we will study in this lab. One is the change in concentration. All these 1, 2, 3 summarizes change in concentration. What you see here, probably in your text, the teachers talk about change in concentration, but are broken down in such a way that you can really answer a question in exam based on how the question is tailored, all right? Change in concentration can be 1, 2, 3, 4. Which concentration are you changing? Is it product? Is it reagent? And the arrows help you in configuring your mind where the system will shift. I know some of you, you may be aware of how the system will respond with those, but if not, I will take notes and make my own notes, read the text if you are taking the course right now, so that you know how to answer the question on changing the concentration. Now, I don't want to get into increase in pressure or change in pressure. Maybe I should have said that this is change in pressure, because pressure can be decreased or increased by changing the volume. So here, I'll just leave this to you. I don't want to change in pressure. Anybody want me to go through the change in pressure? If you feel like you need, this is the opportunity. I can just real quick dive into pressure, but if not, I'm just gonna move on to 6, which is relevant to what we are doing today. Any question? Do you feel like you need me to go through the pressure? If not, I will go to stress number 6, when we change the temperature. When we change the temperature. All right, looking at the temperature, I'm just going to write first of all the equation, or thermochemical equation indicates. This is a thermochemical equation. All right, hydrogen gas plus oxygen, not oxygen, but nitrogen. I meant to say nitrogen gas nitrogen gas to produce ammonia, NH3 gas there. We got to balance the equation, put a 2 there and put a 3 there. The equation is balanced. The equation is balanced. You may see that delta H right here equals to negative. Let me just put 17 there. Negative. This is negative. What does that mean? Is it exothermic or endothermic? Is it endothermic or exothermic? When you have delta H being negative value, is it exothermic or endothermic? Is it exothermic or endothermic? Look, is it exothermic or endothermic? You can use the chart feature, please. Look, is it exothermic or endothermic? Is it exothermic or endothermic? Yes, it is exothermic, Adam. You're right, it is exothermic. Delta H, if you have delta H here, being positive, it is endothermic. If it is negative, it is exothermic. You have to understand what this exothermic, endothermic means. Once you figure it out that, you can now write the heat content on where it is. I can rewrite this, my example here, I will rewrite it now as 3H2 gas like that, plus nitrogen gas, plus, no, not plus, but going to, this is going to produce 2 moles of ammonia gas. And I will rewrite now, look at what I'm doing, plus, I can say heat, all right, because it is exothermic. It is exothermic. If it is endothermic, I'll just write that as 3H2 gas plus N2 gas going to, no, plus heat on this side. This is exothermic, giving me 2NH3 gas. This is endothermic. That means they absorb heat from the surrounding. If you hold an exothermic reaction, if this is a reaction vessel and the reaction is exothermic, if I hold it, it will feel cold because it's absorbing heat from my hand and I feel it cold, right? Now, if it is, that is endothermic. If it is exothermic, holding a reaction flask for exothermic, it will feel warm or hot because heat is being given off. With that, rewriting the equation, including the heat in thermochemical equation should explain how the reaction will, you treat the heat as if it is a reagent or if it is a product. In this one, exothermic, this is exothermic right here. This is exothermic right here. That means it's giving away heat. We treat now heat as a product in exothermic reaction. If we place this reaction here, let me call this A here. If we place it in ice bath, if we take this place in ice bath, that means we are removing the heat on the product side. And remember what we say, changing the concentration of the product. We treat heat as a product. And if we put it in an ice bath, if we chill the reaction, the system will shift in that direction to replenish what we are removing by cooling it. If we increase the heat by placing in water bath, it will shift in this direction. So increasing the heat by placing in the water bath, it will shift on the left side or towards the reactant side because we are stressing the system by increasing the heat, all right? Increasing the heat. And from there, you can make a conclusion on what will happen. I've seen questions that if you increase this, that means you're gonna, all right, if you increase it here, this will go down, this will go up, this will go up, because more of this will be produced, more of that will be produced. I've seen technical questions saying that suppose I increase it, the concentration of nitrogen gas will decrease. No, the concentration of nitrogen gas will increase. Or which one of the following is true if we did this in what? In a thermodynamic or a thermochemical reaction. So for endothermic, it works the same way. If we increase the heat, it will shift in this direction, increasing the heat. Let me just say increasing, all right? Increasing heat. This is for exothermic. And if we in that direction, that means decreasing what? Decreasing the heat. Decreasing the heat, it will shift in that direction. We treat heat as if it is a reagent in exothermic reaction, and the system will shift in either way depending on what you are doing with the heat. This is changing in temperature. Is it going to shift in this direction? If you are increasing, yes. If you are decreasing, it will shift in this direction. So, well, if I put, for example, let me just put here and say this is, maybe call this yellow, all right? If yellow here, and let me just change the equation here. We don't have that. We don't even have this, all right? And we don't have this right here. And if I put here as right here, this is, let me say this is orange right here, orange. And here is, we know heat is either evolved or either heat is produced in the reaction, or either heat is absorbed or heat energy is absorbed during the chemical reaction. One of the objective, there are two objectives in today's lab, is to identify which, all right, is to identify whether the reaction is exothermic or endothermic. If you are given heat or given these enthalpy of reaction values right here, just the way I asked earlier on, it's very easy to identify whether it is exothermic or endothermic if you see the numerical value, negative exothermic, positive endothermic. But in our lab, we will perform an experiment to determine whether we're gonna add heat on this side or we're gonna add heat on the product side. What will be our guiding or our reference is the color change, right here, is the color change. All right, is the color change. Suppose, let me give you this right here. Adding, placing in an ice pan. Let me just erase this. Ice pack. You notice that there's intense yellow color. Placing in hot, maybe warm or hot. Let me just put it here. Warm, this is warm water path. Orange color increase, or you notice that. And you are asked upon performing this experiment, yeah, just, you know, 2 steps in performing the experiment, what will be our conclusion? Is the reaction exothermic or endothermic? Which part of the equation are you going to add the heat? Is it product or reagent? The color coding here will be your hint. Normally, you know, I take points off whenever I ask students to give me the dynamic equilibrium expression without indicating the color. You need to indicate the color, because how will you know that it's going to shift on this direction or on this direction? It's based on the color of your reactants or product. In this case, we will look at what? We will look at the yellow, we will look at the orange. Let's see. If we place on ice path, we see this color. That means it will shift in this direction. All right, ice path, it's gonna go in this direction. If we place in water path, it's gonna shift in this direction. With that conclusion, that means heat will be here, plus heat. Let me show you why. You see, in placing in an ice path, yellow color, that means you are removing what? You are removing heat, and it will shift in this direction, and more of this will be produced, more of this will be produced, while the system is trying to replenish whatever you are removing. So it's gonna shift in this direction. Removing a reagent will shift in that direction. Removing the heat will shift in this direction. Removing could be either in chilling or, you know, placing in an ice pack. You may not see the wording remove heat or add heat, you know, but based on the steps or the experiment, you should be able to see where the system will shift. If you look at the second procedure or activity, place, all right, placing in water path. And orange, this is orange color. This orange color increase. That means if we place this system at equilibrium in warm water path, we are increasing the heat, and the system will shift in such a way we are stressing the system. In a similar fashion, in objective number 2 for today's lab, you will be able to, or you should be able to determine which side of the thermodynamic, all right, which side of the thermodynamic or thermochemical equation will you place, or should you place the heat in order to make a conclusion. So there are 2 objectives for today. It's not about this 6 or 8 stresses. I'm not going to talk about adding a catalyst. You can read on your own. I'm not going to talk about what happened when you add inert gas. If you look at the 8 stresses right there, if you didn't know there were 8 stresses, please just go and make your own notes. If you can have 8 papers, full scopes, or, you know, printer papers, each of them explaining how the system will respond if you subject to these stresses I just went through. So here are, this is what you'll be looking at. What I'm using as a check mark is probably what you will have to investigate in today's lab, all right? In today's lab, you will have to look at the change in concentration, all right? and the change in or effect of change in temperature, in a system at equilibrium, So in part or activity one, all right, activity one, activity two, and activity three, that means change in concentration. There is activity one, activity two, and activity three. All right. This has to do with change in concentration, activity four is the effect of temperature. All right. Effect of temperature. And I just talked about the temperature on how the system will respond. So your job is to perform the experiment and see where the system will shift. If you you should take a picture of each and every step mentioned in the lab procedure, so that when you add or you should attach, okay, for table 1 and table 2. Table 2 is the effect of temperature. Table 1 is for change in concentration, And you will be using, just the way I showed you, you will be using the thermodynamic or thermochemical equation. Believe this is the data sheet. Should have shown you the data sheet on the lab procedure on what you will be doing, or the thermodynamic equation for cobalt. All right, for cobalt 2 chloride. All right, cobalt 2 chloride. The equilibrium expression is shown on page. I want to show you the page with the equation you're going to use. It is on page 4. Page 4 in all right. Page 4 in the handout, and here is, all right. Here is the dynamic equilibrium expression. If you don't have the handout with you, I see this copper 2, this is H2O, 6 moles of H2O, and this is aqueous with an overall charge of +2 plus 4 Cl negative in dynamic equilibrium with copper 4 aqueous plus 6H2O. This is 6H2O. What I wanted to point out is this is blue. This is blue, and this is green. This is green. The color coding, you should pay attention to make a conclusion where the system will shift, all right? Where the system will shift. I've explained how the system responds when you change the concentration, changing the concentration. With that, that is just an overview of what you will be doing in this lab. I want to just take a minute and ask if there's any question. If there is no question, and then you should be able to follow the direction. It is pretty straightforward. I know from the lecture we have started this, it's easy. It's easy, this should be easy. And by the way, Chem2 is all about dynamic equilibrium. From this point on, the experiment will revolve around dynamic equilibrium, all the way, all right? Even in the lecture, it's gonna go from chapter 15 all the way to chapter 19 is dynamic equilibrium. Adam, by the way, the PostLab file is the same as pre-lab. Okay, thank you. I'll fix that, and you know, it's due next week. Maybe I was doing last night, or I made a mistake, and that's why I put that. I'll put a post lab, the correct post lab for this experiment number 6, so that you can do it turn in by next week. Other than that, is there any other question? If there is no other question, I expect you to this lab data sheet due next week, and the post lab as well. Look at the pre-lab by tonight. I've created some of you who have turned in. I've started working on or creating your pre-lab for this lab. So make sure you turn in by midnight today if you haven't turned in the pre-lab for lab number 6. Shortly, I'll make lab number 7 data sheet and instruction available for you. It is a simulation for next week. Experiment number 7, calculating the equilibrium constant of cobalt to chloride. It will be a simulation. I'll send out the instruction as well for next week along with the pre-lab. Other than that, I'll stop sharing my screen, and we will meet again next week, same time. All right. If there is no other question, I will stop sharing my screen and end the lecture. Thank you for tuning in today. I hope to see you next week. Thank you. Be safe. See you next week.